So let us take a conductor. Let us take a conductor, and we know that the conductor has large number of free electrons. So this is my conductor. This is a conductor, or you can say it's a piece of wire. A piece of wire. A piece of wire. Okay. And it has large number of free electrons. Large number of free electrons. Large number of free electrons. Free electrons. Okay, so it has large number of free electrons. Now, if I connect this conductor with the help of some battery, and this is the positive terminal of the battery, it is negative terminal. So voltage of the battery is V. So let me take the voltage of the battery is V. This is a V volt. So we know that this side will become positive and this side will become negative. And electron, they will start drifting from negative terminal to the positive terminal. So the direction of drift of the electron, that is from negative terminal to the positive terminal. So these small arrows, they represent the direction of motion of the electron. And we know that the current in this wire, that will flow in a direction opposite to the direction of flow of electrons. So the current will flow in this direction. This is the direction of current, just opposite to the direction of flow of electrons. So this is the current I flowing. So this is the experimental law, and from this law we can draw a table. We can draw a table between voltage and current. Between voltage and current, we can draw a table, yes. So here I take the voltage and here I take the current. The voltage is in volt, it is in volt, and current is in ampere. Current it is in ampere. So in the first reading, when voltage is 0, means no battery is connected, then there is no current. There is no current. When voltage is 0, the current is 0. When there is no battery here, then it means the flow of electron. The flow of electron is there, but the electrons, they are moving in a random direction. So the effective current is 0. When the electrons are moving randomly, so they will contribute zero current. Zero current. Okay. In the second case, when I apply certain voltage, suppose it is 0.1 volt, then I get certain current, and let me assume the current is 0.1 ampere. So when again I increase the voltage from 0.1 to 0.2, I find the corresponding change in the current. So what I observe in my experiment, whatever change is there in the voltage, the same change is there in the current. So the current changes according to the voltage. Current changes according to the voltage. According to voltage. So from this statement, the current changes according to the voltage, or I can say current changes in proportion to the current, in proportion to the current. So whatever change, whatever jump, whatever shift is there in the voltage, the corresponding shift we will observe in the current. So from these two statements, I can make a relation between voltage and current. So we can say voltage is proportional to current, and we can write V is proportional to I, and this proportionality is replaced by equality by introducing a constant, and this I remains same, and that constant, particularly in this case, is resistance. It is called resistance. So R basically it is the resistance of the conductor, or resistance of the wire, or the resistance of the material we are taking in this experiment. So this relation V is equal to IR, or we can write it also, or it can be written as I is equal to V upon R. So this relation and this relation in terms of voltage, this is in terms of current. So this is called Ohm's law. Ohm's law, because this was experimentally observed by the scientist Ohm. So on the basis of his name, it is called Ohm's law. So it's nothing, it's a relation between voltage and current, and the change in the voltage that gives a change in the current, and both are proportional. Whatever change is there in the voltage, the same change is observed in the current. So this is called the Ohm's law. Now if we plot a graph between voltage and current, so let me take, this is x-axis and this is y-axis. On x-axis, I will take the voltage. And on y-axis, I take the current. So when both voltage and current are zero, from this graph we can see that voltage is zero, the current is zero. So here I plot voltage is equal to 0.1 volt, 0.2 volt, 0.3 volt, and here the current is 0.1 ampere, 0.2 ampere, 0.3 ampere, and so on. So what we observe, when it is 0.1, the voltage is also 0.1. So 0.1. So I can just make a point over here. Similarly, it is 0.2. So it is also 0.2 when it is 0.3. So current is also 0.3. So now by joining these points, I can draw a straight line passing through the origin. And this straight line, it's nothing but it's the resistance of the wire. The straight line that gives resistance of the material used in this experiment. So basically, this straight line that shows a linear relation between linear relation between voltage and current, between V and I. It gives a linear relation, right? Ohm's law is not a universal law. It's not a universal law. So note this point. Note this point. It's not a universal law. यूनिवर्सल लॉ क्या होगा? यूनिवर्सल लॉ अगर ये होता तो कोई भी मटेरियल यूज करते उसमें वोल्टेज और करंट का सेम ग्राफ हमें मिलना चाहिए था। कोई भी मटेरियल यूज करते, मेटल यूज करते तो उसमें तो देखो हमें मिला ही है, बट अगर नॉन मेटल यूज करें तो क्या उसमें भी यही ग्राफ मिलेगा? क्या सेमीकंडक्टर मिले क्या उसमें भी यही ग्राफ मिलेगा? या किसी तरह का कोई कंपाउंड मटेरियल लें उसमें भी यही ग्राफ मिलेगा? किसी तरह का कोई अमॉर्फस मटेरियल लें उसमें भी क्या यही ग्राफ मिलेगा? नो, अलग अलग मटेरियल्स के ग्राफ अलग अलग मिलेंगे। अलग अलग मटेरियल की जो इलेक्ट्रिकल प्रॉपर्टीज हैं वो अलग अलग हैं। सो अलग अलग मटेरियल्स के लिए करंट वर्सेस वोल्टेज का ग्राफ भी अलग अलग होगा। सो इसमें हमें मेटल्स में और कंडक्टर में हमें एक लीनियर रिलेशन मिला, एक स्ट्रेट लाइन मिला। बट इफ वी टेक अदर मटेरियल्स, if we take the semiconductor material, and in the semiconductor material if we plot the graph, then we will get a non-linear curve. We will get a curve which is non-linear. So we will get a curve like this. So this is for semiconductor. So for different materials, the graph between voltage and current are different. So Ohm's law is not a universal law. So this is the main point which is to be noted. It's not a universal law. And the relation, this relation can also be written in one more form. We can write R is equal to V upon I. R is equal to V upon I. So if we take voltage V is equal to 1 volt, V is equal to 1 volt, current is equal to 1 ampere, this is 1 volt, and this is 1 ampere. So R becomes, R is equal to 1 upon 1 is equal to 1. This is called 1 ohm. So what is the definition of 1 ohm? 1 ohm is that resistance, 1 ohm is that much resistance offered by a wire when it is connected to a voltage source of 1 volt, which produces a current of 1 ampere in the wire, right? So resistance is said to be 1 ohm when voltage applied is 1 volt and current flown through the wire is 1 ampere. So this is the definition of 1 ohm, right? So now if we take two different conductors, two different metals, so and I plot a graph of V versus I, V versus I, and this is my origin. This is for metal A, this is for metal B. So हमें पूछा गया है कि मेटल A और मेटल B में रेजिस्टेंस किसका ज्यादा होगा? So definitely more is the slope, more is the resistance. So slope of A is greater than slope of B. So we can say resistance of metal A is greater than resistance of metal B. So basically it is the slope which will decide the resistance. More is the slope, more is the resistance. So अगर ऐसा ग्राफ हमें पूछा जाए कि दो मेटल्स हैं A and B, दोनों में रेजिस्टेंस किसका ज्यादा होगा? सो जिसका स्लोप ज्यादा होगा उसका रेजिस्टेंस भी ज्यादा होगा, राइट? So now we take another case which is called electrical resistivity and conductivity. Electrical resistivity and conductivity. So our next topic is electrical resistivity and conductivity. So we will derive electrical resistivity and conductivity from Ohm's law. From Ohm's law. From Ohm's law. So let us take a conductor. Let us take a conductor, and this is my conductor, and length of the conductor is L. Length of the conductor is L, and it is connected to a voltage source. It is connected to a voltage source having the voltage V. This is positive terminal, this is negative terminal, this will become positive, this will become negative, and the electron inside the conductor, they will start moving from negative terminal to positive terminal, and the current that will flow from positive to negative terminal I, right? So we know that these electrons, they will accelerate, and acceleration of the electrons that is given by A is equal to F upon M. And we also know that the force on each electron that can be written as E into E, where E is the charge on the electron and this capital E is the electric field. So here the electric field is from positive to negative. Always the direction of electric field is from positive to negative. So this is my electric field. E is the charge on the electron and this is M. And we can also write E is equal to, E can be written as V upon L, where V is the voltage, this voltage, L is the length of the conductor. So now I can replace this E by V upon L. So what I get, acceleration is equal to E upon M into V upon L, V upon L. So let me call this is my equation number 1, right? And we also know that these electrons, they are accelerating from negative terminal to the positive terminal. Along with the acceleration, they also possess drift velocity. So the drift velocity of the electrons, drift velocity, we know VD is the drift velocity, that is equal to acceleration into relaxation time tau, right? So let me call this is my equation number 2. And we also know that the drift velocity can also be written in terms of current. So now I will write drift velocity in terms of current. Drift velocity in terms of current. So we know that current I is equal to N, A, E, and VD. So from this, I can find this VD. So VD, drift velocity, is equal to I upon N, A, E, where I is the current flowing in the wire, N is the total number of electron in the wire, is the area, cross-sectional area, this area. This is the area, cross-sectional area A, and E is the charge on the electron. And you know that charge on the electron, it is 1.6 into 10 raised to the power minus 19 coulomb. So this is the drift velocity, and let me call this is my equation number 3. Now I will compare equation number 2 and equation number 3. So comparing the two equation 2 and equation 3. Comparing equation number 2 and equation number 3. So what I get? You see, left hand side they are equal, so I can equate the right hand side also. So equating the right hand side, so A tau is equal to I upon N A into E. Now, putting the value of A from equation number 1, let me call this is my equation number 4, and put the value of acceleration from 1 in 4. Put value of A acceleration from equation 1 to equation 4. So what I get? E by M V upon L into tau is equal to I upon N A into E. Right? Now, my target is to find out this V. My target is to find out this V. So I will try to find out this voltage V. This V. This is my target. So how to find this? So V can be written as V is equal to, this can be written as V is equal to M upon N square tau, N E square into tau L upon A into I. So I can write V. So this is my V. This is my V. Now I got the value of voltage. So let me call this is my equation number 5. Equation 5. Right? We also know that from Ohm's law, V is equal to R into I. So let me call this is my equation number 6. Now comparing equation 5 and 6. Comparing equation 5 with 6. So what we observe that V is there in equation number 5, V is there in equation number 6, I is there in equation number 5, and I is there in the equation number 6. Now what is this intermediate term? So it means these intermediate terms that can be compared by this R. So I can write now R is equal to, so R can be written as R is equal to M upon N E square into tau L upon A. So this is the equation for resistance of the wire And from this equation, we can see that m is the mass of the electron, n is the total number of electron, E is the charge on the electron, L is the length of the conductor, A is the area of the conductor. So now we can conclude that if we bend this wire into any shape, suppose I convert this wire into L shape or M shape or S shape. So by bending the wire in any shape, it is not going to change the resistance of the wire, because when we will bend the wire, overall area will remain same, it is not going to change. Length of the wire, again it is not going to change. Inside electrons, they have mass m, again the mass, that is also not going to change. The total number of electron, that is also not going to change. The charge on the electron, also it is not going to change. Relaxation time, the collision, the time between the two successive collisions, also again it is not going to change. So from here I can say that if we bend the wire into any shape, it is not going to change the resistance. Okay, so from here I can conclude that by changing the bending, or we do anything with the wire, it is not going to change the resistance of the wire. So the resistance of the wire, basically it is determined by total number of electrons. So resistance of the wire, basically it is determined by the total number of electrons in the wire. If the total number of electrons they decreases, if the total number of electrons that decreases, that resistance of the wire that increases. If the total number of electrons that increases, the resistance of the wire that decreases. So basically, I can say that resistance of the wire is inversely proportional to total number of electrons. So this is the relation between, so what is the factor on which the resistance of the wire that depends? The resistance of the wire of any conductor of any wire, that depends upon the total number of electrons present in the wire. More are the electron, less is the resistance. Less are the electron, more is the resistance. So again, the relaxation time does not change because electrons have negligible inertia, and so their drift velocity does not change. So when we bend the wire, again relaxation time also it is not going to change. When we bend the wire, or wire is straight, wire is bent into any shape, the collision time again that is remain unaffected. So resistance remains unaffected. So the only thing on which the resistance of the wire depends, it is the total number of electrons present in the wire. Resistance is inversely proportional to total number of electrons. So that's all. So it is my first lecture. Okay, so I will just finish this lecture over here. Okay.
Thank you.